Ok, l'ho registrato adesso. Okay, so this is the last lecture, and I was thinking maybe I'm going to keep it a little bit shorter. So I want to continue with what we were talking about last time, which was this problem of understanding the structure of the set of rational varieties in families. So what we did last time was to study, so we proved that on a smooth family, the set of rational varieties form a countable union of closed sets. And the question is, what happens if you allow singularities in the fibers? So what happens if you have a family of rational varieties and then you let it degenerate to some singular variety? So what you see, for instance, is that the theorem that we proved last time don't generalize certainly completely in obvious way. So for instance, let me just start with a very basic, simple example. You just consider a case of a family of smooth cubic surfaces. So these cubic surfaces inside P3, and you let degenerate to the cone in the projective space, the cone over an elliptic curve. And clearly, so the cubic surfaces of the complex numbers, those are rational. But the cone of an elliptic curve, E, it is not rational. Okay, so I want to look at this example and try to see if there is some condition we can put on the special fiber which get rid of this example and maybe allows to generalize the theorem, so we can conclude that the central fiber is also rational, even though maybe there are some singularities. So I want to talk about two results in this direction. The first one is also in the work in this paper by Kontsevich and Shinko. So this is a notion of B rational singularities. So B is not like birational. B is, I believe, stands for Burnside, which is the group, the construction they use to construct the specialization map. So let me start with the definition. The first thing I want to do here is to extend the definition of the Burnside group a little bit. So suppose that S is where they say separated scheme of finite type over a field, okay? And then you define the following version of the Burnside group. And it depends on S over K. So what is this? This is a Grothendieck group generated by field extensions. Oh, so it's finitely generated. Or maybe I need to add this in the notes. Finitely generated field extensions L over K, they're equipped with a morphism from spec L to S. Of course, the morphism is over spec K. So another way of thinking about this is that this parameterizes this Weil points on a scheme. Weil points is just a map from a field to S over the ground field. Okay, and then this modulo isomorphism over S. Okay, meaning this diagram, a modulo isomorphism on this diagram. So given an L for any L as this, as above, we got denote the element S over, sorry, L over S will be the corresponding element in this group. Okay, and then again, there is a grading. So this group is a graded group. Okay, but the grading is given by transcendence degree over K. And then this construction is functorial. So if I give you a map between two schemes, G, this of course is defined over spec K. And to this map, we can associate it, a push forward map from the Burnside ring over S prime to the Burnside ring over S. Just by composing the map from spec L to S prime with a map from with G. And this is a graded group homomorphism. Okay. So the idea of this construction is that I want to now allow singularities, but I want to say the singularities are irrelevant from the point of view of the computation of the specialization map that we discussed last time. And so we phrase this in the following way. So this here is a theorem. This again, Kontsevich and Shinko. Suppose X is an n-dimensional variety. Again, we now go back to walk over the complex numbers, although this definition, again, I stress this definition definitely more general, but in application that we're going to see, we're going to work with complex numbers. And now suppose that inside here, I look at Z to be a proper closed subscheme. We can assume it's reduced because the definition will not see the scheme structure beside the reduced underlying subscheme. And then we define, so for every X and this, we can associate to the pair XC an element which I denote by D the ZX in the Burnside group over Z. And now back to complex numbers, and this will be in dimension n-1. So maybe let me write this better. Okay, with the following properties, so the first property I want here is that we can compute this when when Z is a simple normal crossing divisor. So if X is smooth and Z is a simple normal crossing divisor, then I want this element to be defined as follows. So you notice now that this definition looks very familiar. So I'm going to take alternating sum, depending on the size of the index set, -1, of what? Of the class of some field Li relative to Z, where, as before, first of all, let me define by eta I inside the I, which is just the stratum here, is a generic point. of the stratum, and Li is just a field, transcendental field extension, pure transcendental field extension of the residue field of the stratum. So I just need to add enough variables to bring the dimension to the right place. And that's the number of variables I need to add. Okay. So it's exactly the same formula that we gave in the theorem last time to define a specialization map. So you see how this definition will be tailored for the purpose that we're going to discuss next. The only difference here is I can do things in a finer way by not just taking the class of these field extensions over K, but also remembering where the generic point of the stratum is inside Z. So is there some additional marking that is useful to avoid unwanted cancellations. And then the second property I want is that, so if you have a supernormal crossing pair, so X is smooth and Z is a supernormal crossing divisor, then this is what we want it to be. And in general, I want to satisfy the following properties. If G from X prime to X is a log resolution of the pair XC, and we set Z prime to be the inverse image of Z under this log resolution. And again, it doesn't really matter whether you want to regard Z prime as a schematic inverse image or just a set theoretic inverse image. Then we want that this class associated to the pair XC to be the same up to the push forward. So maybe I restrict G to Z prime and push forward the class computed on the log resolution, which is computed by the formula they just gave in the first condition. Okay, so if you think about this, part one is telling you how to compute this class in a supernormal crossing situation, and the part two is telling you how to compute it in general. So you note by resolution of singularities, 1 and 2 give a definition of this element in general. The only thing to check is that in definition, so you need to check that this is independent of the choice of resolution. But this is done by the same kind of computation that we did last time in showing that the specialization map was independent of the choice of resolution. So you just need to pick up two different log resolutions and then apply the weak factorization theorem to go from one to the other. And then you study one blow up at a time.
So Tommaso.
Yes.
What happens in the first property?
Yes.
No, first property. What happens if Z is non-reduced?
Yes, exactly. So how you see from here is maybe let me make a small correction. I think maybe this is a best way to answer this question. Instead of Z, assuming that Z is reduced, let me just assume that the reduced subscheme of Z is a simple normal crossing divisor.
Mm-hmm.
Yeah, that's maybe a better way of writing it. So I want to give a definition that doesn't see the reduced structure, the non-reduced structure of C.
But also then in the second part, if it doesn't see, so if two schemes have the same support.
If two things have the same support, then they define the same element.
Okay.
Yes. So let me make this as a remark, yeah. Definition of this element does not see schematic structure. But only. In fact, to be honest, I think that the best way of writing this definition, maybe I should do that. The best way of writing this definition is just not assuming that Z is an arbitrary scheme, but just assuming that Z is a reduced scheme, a closed, like a closed set, interpreted as a viewed as a reduced scheme, and then and then we can, when we take the inverse image, we take the inverse image with the reduced structure. I think that maybe because it doesn't really matter this kind of things of looking at schemes only from the point only the reduced structure is kind of common in these situations. For instance, if you define a Grothendieck group of varieties, sometimes you want to work with schemes, but the Grothendieck group also will not see the no reduced structure of a scheme. So it's kind of consistent with that. Okay, so now let me give you the main definition here. So let X be a variety. And Z inside X, closed subvariety of codimension 1. The pair XC is said to have B rational singularities if this element defined by the pair we just defined above, it just computed by one stratum of Z, which is the after resolution, which is the one coming from Z itself, so the proper transform, if you like, in the log resolution. And this is just computed by the function field of Z viewed over with a map to Z itself, mapping to the generic point of Z. In this ring. Okay, so let me give an example. And this example will take us back, then after this example, we can look back at this other situation of cubic surfaces degenerating to a cone of an elliptic curve. Okay. So assume X is smooth and Z inside X is codimension 1 subvariety with an ordinary multiple point. At some point P has only singularities. So what does it mean this? By this, I mean that if you look at the tangent cone as Z at P, this is a smooth away from the vertex. Or equivalently, that if you blow up if you blow up the maximal ideal, the exception divisor, when you blow up the maximal ideal of the point, the exception divisor with the scheme structure is reduced and is a smooth variety. So I think the technical term for this point is also known as quasi-homogeneous singularities. In fact, I don't know how standard the terminology ordinary multiple point is. So what do we have in this situation? So yes.
So you said, so this ordinary double point, we can resolve it by blowing up this maximal ideal, but it's not a normal blow up. So the exceptional set is not just a P1.
No, the set, let me actually, I'm gonna explain exactly this right now.
Okay.
So so let me explain exactly this blow up. So you have X here, and what we do is that we blow up point P. So this gives you a variety X tilde. Inside here, there is a divisor E, which is equal to some P n minus 1 if n is the dimension of X. Inside X, I have Z. So if I take the blow up of Z at P, I get the Cartesian square here. Like that. And I have a divisor inside here. So let me call this map G, the blow up of X. So, and now this condition is, let me actually move this a little bit. The condition here is that F inside E is a smooth upper surface. And the degree of F will be exactly the multiplicity of the point on Z. And moreover, if I look at the proper transform of Z, the blow up of Z, and I intersect with E, this is EF, and this intersection is transversal. So another way of saying is that this F is cut out scheme theoretically as a reduced intersection. Okay. So of course, F is if Z is smooth, then F will be another plane. Inside E, if E is an ordinary double point, if P is an ordinary double point, then F will be a smooth quadric inside E. But in general, it could have a high multiplicity. So essentially, what you do is that you look at a local equation in some coordinates, and you look at the leading term, the term's homogeneous degree, smallest homogeneous degree, and that homogeneous term is give you the equation of F. So I can also do a picture. So you have X here, and then there is this P, and this is how Z looks inside X. And now what you do is that we are blowing up the point P. So when we blow up the point P, we extract a divisor E, which is some projective space, and Z is going to proper transform Z tilde, which is the blow up of Z at point P. It will intersect along some F, which is embedded, and the intersection is transversal. So in particular, what you see is this G is a log resolution of the pair XZ, and the pullback or inverse image of Z is just Z tilde plus E. Okay, maybe with some multiplicity. So maybe right in this way, the inverse image of Z with maybe with a reduced structure is just Z tilde union E. So now how many strata do I have here to compute the class? I have 3 strata because I have Z tilde, I have E, and then I have F, which is the intersection of the 2. So now we just compute it. This element, I computed on X tilde, which is a push forward of the corresponding element. Let me call it Z prime, and Z prime of X tilde. So when I compute, I just need to look at the fields, at the function field of this piece, the function field of this piece, and then I need to subtract the function field from F. And then I regard them with a map. So this map to the generic point of Z, and these 2 pieces here, they both map over P. So I remember those maps. So this will be equal to, well, I have the function field of Z from the first stratum, regarded with a map to Z. And then I have the function field of E with a map to Z. And then I need to subtract the function field of F, to which I add some variable to make it of the right transcendental degree, transcendence degree, again, regarded over Z. And these two actually over the point P inside Z. So the map maps a factor to the point P. So the first term is what we want, and the second term is what we want to cancel out. But this guy, this is rational. This is a projective space, so that field is just is a field of a rational variety. So the only way I get a cancellation, what I see here is that I need to understand what happened to this guy. In order to make a cancellation with other fields, I see that this pair XZ is by rational singularities if and only if F cross P1 is rational. So that's a condition on F. So for instance, if P inside Z is an ordinary double point, which means that F inside E is a smooth quadric, then F cross P1 is rational. Hence, XZ has birational singularities. On the other hand, if Z is a cone over an elliptic curve, and P is inside Z is a vertex, then F is just isomorphic to the elliptic curve. So F cross P1 is not rational. Hence, XZ is not doesn't have birational singularities. Okay. Let me give another example.
Excuse me, Tommaso, just a small question. The fact F cross P1, does it is related to, maybe I'm wrong, stable rationality, you know?
Exactly. So
okay.
This condition here implies that F is stably rational. So stably rational means that after you multiply by some projective space, it becomes rational. Maybe multiply by P1 is enough. Maybe it's not. Maybe you need to multiply a little more. But the idea is that after you multiply by some projective space, it becomes rational. In particular, if it becomes rational after multiplication by P1, then it is stably rational. Yeah, absolutely. But the stable rationality is going to come up again in a moment. So give you another example. Look at a pair XZ where X is a smooth surface, AG x is equal to maybe a2, and z is an irreducible curve, possibly singular. Okay, then the assertion here is that then the pair xz has be rational singularities if and only if the curve z is unibranched at its singular points. And the reason is that if I just look at one singularity, so if the curve has several branches along the singularities, or one branch or maybe several, maybe come back again and so on. So what I see is that what you need to do here is you take some log resolution, because the curve, the surface is smooth, a log resolution will be given by some three irrational curves. But then along these two irrational curves, I need to also, I find also the proper trisom of the curve z. And now the question is how many points I'm subtracting of the intersection I have. So, and again, it boils down to a combinatorial statement in which I just compute all the characteristics of a dual complex. So, it's all the characteristics of the dual complex of the pullback of z tilde minus the proper trisom of z tilde, so minus a point. And I want this sum to be 0 because all the curves and the points are equivalent in the Burnside group, because the curves are all rational curves and the points are extended by one variable. So they all cancel out. The only thing I need to assure is that there is a right number of points given the number of coordinate components. Okay. So now the theorem that I prove using this definition is the following generalization. So suppose the f from x to c is what? Let me just assume this. Suppose that this is a family of proper or projective varieties. Or a smooth curve. Now assume x eta is rational over the function field of the curve, and for some close point in the curve, the pair x with the fiber over this point has the rational singularities. Then the central fiber is rational. So we allow, for instance, again, if I degenerate to the central fiber has ordinary double points and the total space of the family is smooth, then I can apply this theorem. But if the central fiber has the corner of an elliptic curve and the total space of the family is singular, so it's still smooth, then I cannot apply the theorem. Doesn't apply. So the proof of this is just the observation and the definition of a rational singularity is tailored to extend the proof from the smooth case. I mean, we proved this theorem when assuming that F was a smooth vibration. Now F is not necessarily a smooth vibration. I need to worry about the singularities, but the definition of B-rational singularity is exactly what I need to just take the same proof and adapt it to get this statement. Any questions on this?
Not
definition of family for you is flat and proper.
Yes. So yeah, it's a flat family. X is a variety. I'm assuming I started assuming projective. It doesn't really matter too much. Proper.
Do we need properness again for this push forward that we used above?
No.
Okay.
But we need properness for this theorem. Because if I don't have a proper family, I don't know what's happening when I take a closure. It could get very complicated.
Thank you.
So,
Yeah.
so this is not an if and only if.
No. Of course not.
Only a sufficient condition.
Yes.
In this sense, it looks a bit weak.
Yeah, of course. On the other hand, I think even the smooth case, I mean, was a big. I mean, I thought it was a very beautiful theorem because this question of understanding specialization of rational varieties in smooth families has been open. I think people thought about this maybe 100 years ago. Although I don't really have a reference for that, but I would imagine that it's such a natural question, and it came up with such an easy answer after. No. Okay, so 8.2. So the next talk I want to talk about, the next thing is I want to talk about is the following. Talk about the case of threefolds. Okay, so back to the example. Again, you look at the smooth cubic surfaces degenerate to a cone over an elliptic curve. Okay, so is there some other ways we can, so now this theorem of this notion of B-rationality or B-rational singularity is already one way of excluding this example because the vertex of this example doesn't satisfy that. But is there another way that we can look at this example and say that, of course, we cannot expect rationality here. Maybe some other condition, some other necessary property that we can look at as and ask whether it's a sufficient property. So the point here is that in this example, the central fiber is not rationally connected. So what does it mean rationally connected? Suppose that I have a B, some proper variety or projective variety. So what does it mean to be rationally connected? It means that if for every two very general points, P and Q, so I pick 2 points here, P and Q, very general just means that they're chosen away from countably many close conditions. So if you like, look at the symmetric product square of V and just look at countable union of proper closed subsets and then pick P and Q inside there away from this locus. So for me, there exists a map F from P1 to V such that F of 0, one point in P1 is equal to P, and F of another point called infinity is equal to Q. So I can join them by some rational curve. And this rational curve is some map F from some P1, the point 0, and the point infinity, and this P1. So there exists such an F, okay, for every P and Q. They are connected by a single rational curve. Maybe as a remark, is that the cone over an elliptic curve is rationally chain connected, but not rationally connected. So what does it mean, rationally chain connected? If I have a cone over anything, in fact, and I pick 2 random points, P and Q, as long as the 2 points are not over the same lines to the vertex, they are not. They might not be rationally connected in this case. Elliptic curves certainly are not, but I can always connect them going to the vertex. I just need 2 lines, so I need a chain in this case. So the rational chain connectedness is a weaker notion, and that we don't want to look at that. So if you have a smooth projective variety, again, over complex numbers, then the rationally chain connected and rationally connectedness are the same condition, because there is some smoothing of chains of rational curves I can do. There is a trick to do that. But over a singular space, the 2 notions are distinct. This is a good example to see that. So what I want to focus about here is the notion of the stronger notion of rational connectedness. So in this example, the central fiber is not rationally connected. So what if we actually ask the central fiber to be rationally connected? Can we actually get a better statement? So one way of thinking about this is that, so notice the rational connectedness. Rationally connected is a necessary property for projective variety or polar variety to be rational. Because I have a rational map, or unirational, in fact. I have a rational map from Pn, take 2 general points, just lift them up, and just take the line to those 2 points. The image would be the desired rational curve. Okay, so we can define the rationally connected locus of a family, again, of projective varieties, to be the following set of points, all the points T and T, such that xt, well, maybe I add the word geometrically, rationally connected. Okay. So this set, so if a family is smooth in characteristic 0, then in fact we can prove that this set is open and closed. So it's either everything or nothing. If I have singularities, I need to be a little more careful, but then you can use the theorem induction to show that this set is constructible. Okay. let's say. Okay. So we have an inclusion of the rational locus of F as a subset of the rationally connected locus of F. So if F is smooth, then the rational locus of F is a countable union of closed sets in T. And in general, we proved this last time. In general, this set is a countable union of locally closed subsets in T. But what if we just regard this rational locus inside the rationally connected locus? Do we actually get closure? Do we get closed sets? So that's the question I want to ask. So the theorem here is that the answer is yes, if the dimension is small. So this is a theorem from with the Fusi. So if F from X to T is a family of relative dimension and at most 3. Of course, the interesting case is when the dimension is 3. Then the rational locus of F is a union of countably many closed subsets or the rationally connected locus. So the key point is that we go back to this word closed rather than locally closed. So in particular, if the fibration, all the fibers are rationally connected, then all this is a countable union of closed sets in T. Okay. So we deduce this from the following specialization theorem. Again, we already know there's some countable constructibility of this locus. And now what we need to do is to prove a specialization theorem when the central fiber is rationally connected. So let me say this next. So suppose I have F as before. So it's a family of relative dimension and at most 3. Oh, sorry. I do this to C over a smooth curve. So assume the central fiber is rational over the field of the curve. Then for every closed point T inside in the curve, every irreducible component D of the fiber over T. I'm not asking, okay, so maybe I need to be, so here maybe I just say allow non-reduced and not irreducible fibers. So maybe I should not use the word family because I've been using family for family of varieties. This is just a morphism. Maybe I should say this more clearly. It's just a morphism. It's a flat morphism. It's projective. from a variety to a curve. But the fibers can be very complicated. I know they are all equidimensional. So, and I look at the residual component, D, of some fiber that is rationally connected and intersect the non-singular locus of X. And in conclusion, this is rational. So let me read it again. I cannot move back and forth. So they say, I assume the central fiber is rational. I look at an arbitrary fiber that could have many components. I pick a one component, and I want to assume two things: it's rationally connected and intersect the smooth locus of the variety. So let me draw a picture. This is X. That's a curve C. I know something about the generic fiber, X theta, which is rational. So this is, and then I look at some other fiber, XT, over a point T, so the generic point eta. And this fiber may have several components. And just look at the components might also be multiple with multiplicity. I just look at one component, one irreducible component. I just want to make sure that it's not fully contained in a single locus of X and is rationally connected. Then the statement is about these components here. In particular, if it's a family of varieties, then the center, the fiber over T will satisfy that because it's reduced, so it has to intersect the smooth locus of X, and then I need to only assume it's rationally connected. Any questions on the statement? Sorry. Okay, so let me prove this. So let's start S is rational. So this implies that there exists a birational map from X to Pn T, which is, remember, just Pn cross T. This map is defined over T, i.e., there is an isomorphism between the field. With isomorphism, go the other way. Doesn't matter. And this isomorphism is defined over the function field of T. Now, we look at D inside X. This is a variety of codimension 1. And I know that in the intersection with the regular locus, the non-singular locus of X is non-empty. So this implies that if I look at the local ring, this is a discrete valuation ring with a divisor evaluation, which defines divisor evaluation, which is denoted by val D, order of vanishing, or I think I call it, actually, I think I used a different notation for this before. Order along D, the order of vanishing along D. It is, I think about this evaluation of the field, of the function field of X. Hence, of the function field of this projective space. Moreover, so this valuation has center in a fiber over the point T, right? I have a point T here. And the center of this valuation in the fiber is contained in a fiber of X over T. And because this isomorphism is defined over here, the center, this valuation is going to have center inside this space, and which lies over a fiber over capital T, over little t again. So over evaluation D has an empty center W inside the space. Because this is property contained in the fiber over little t. I call it order. Okay. So now what we're going to do is that we're going to look at a sequence of blowups. So start from here. You start from this variety, which is smooth. Why not? Then I'm going to take one blow up. G1. And at some point, there's going to be some yi minus 1. Then some gi yi. So I'm going to keep going this way. And so I can tell you what G1 is right away. So this G1 will be the blow up of this W, which I'm going to call it W naught, in the center of the valuation. So here I'm regarding the center of valuation as a closed variety. One can sometimes we use the same word to denote the generic point of the subvariety, which is maybe actually better. But for us, the center is just a subvariety. So I can blow up the subvariety with this reduced scheme structure, just a DO define the subvariety. And let's give me a new model y prime, y1. And then what do I do? The valuation is going to have center over y1 because y1 is proper over y0. And then I blow up that. So in general, what I'm going to do is that this GI inductively is defined as a blow up of yi minus 1 along the center wi minus 1, which is the center over this model for the evaluation order D. Okay. So let me draw a picture. Okay, so maybe the picture I'm going to draw it. Maybe I draw it horizontally. So this is yi, and then I blow up. It's gonna be, this is gonna be, this is yi, and the first one was yi minus 1. So this map is gi. Okay, so what are we blowing up? We are blowing up a center, a subvariety, which is yi minus 1, wi minus 1. And what happens when we blow it up? When we blow it up, we're going to pick up some divisor, which I'm going to call EI, but then there might be some other divisors. So the point here is that yi and wi may be singular. After all, I don't know anything about the center besides being a subvariety. Even at the beginning, y0, w0 is a subvariety in some smooth variety, y0, but the subvariety could have singularities. So if I blow up a singular variety, there is no guarantee that what I get in the blow up is smooth. And in fact, there's no guarantee there is a unique exception divisor. It could have many components. But nevertheless, what you see is that wi minus 1 is generically smooth. And so yi minus 1 will be generically smooth, will be smooth at the generic point of wi minus 1. So what you can see, let me write this, is that you can see inductively that yi minus 1 and wi minus 1 are smooth at the generic point of wi minus 1. And when you blow up, there exists a unique and irreducible component EI or the exceptional locus of GI dominating WI minus 1. So the other components will lie over the singular points of YI minus 1 or WI minus 1. And in fact, this map, which is surjective, is generically as an PR bundle is a projectivization of a normal bundle. Where if I just restrict to an open set where everything is smooth, I'm just blowing up a smooth variety in a smooth variety or smooth variety, and that's the exception divisor will be reducible, and we'll have just a projectivization of the normal bundle. So what I'm saying here is that at least over an open set, there is a nice vibration here going down this way over some open set here. And the fibers of this one are some projective spaces. But in fact, moreover, and this is maybe important if you care about poetic characteristics, is that this is actually really a projectivization of the bundle. So now the key property here that has to do with the divisor evaluations is a lemma-Zariski, which says the following: it says this process stops after 5 many steps. We can find some index I such that at that stage, if I look at the center of the evaluation, will actually be this exception divisor EI. And in fact, if I look at the local ring of YI along EI is equal to the longer ring of X along D, and this is via the isomorphism from the function field of CY to the function field of X. There's a canonical isomorphism given by the birational map, and this isomorphism sends one ring into the other. So one way of thinking about this is that this last blow up has extracted the exception divisor, given the evaluation.
Sorry,
Okay.
could you, how do you define the center of evaluation of the evaluation?
Okay, that's a good question. So I didn't really explain that, but if you have a variety, you have an evaluation ring. So say X is proper for simplicity. Then what you can do is that, well, let me write it this this is, I need to think for a second about this. So a point in X with the property that if I look at the local ring of X at P, this is contained inside the evaluation ring, and P is the restriction, the maximum ideal of the evaluation ring with this local ring. One way of thinking about what this means is that evaluation over a function field, I need to be careful how to define evaluation over the variety, but there will be an open set with a property that every regular function in open set has no negative evaluation. This is already telling you that there's going to be a center inside this open set. And after you do that, then the center will be exactly the ideal generated by those functions where the evaluation actually is strictly positive. So this is defines the center as a point, as a schematic point. If you have an exception divisor on some model and you just look at the image of that divisor, that's defined as a variety. That's a variety. It's exactly the closure of the center when it's defined as a point. And in fact, you see, if you have, for example, if you have a divisor E on some model Y with a map down to X, and you look at W is an image, suppose the W is an image of E, and you look at the generic point of W. So this is the generic point of W, also is what sometimes people call the center. So this is a point inside X. Again, if I just pick an open set, suppose now I restrict to some open set, this is spec A, and now I see that. So this and then there is a point, some prime ideal inside so P is a prime ideal inside A, and then what you can see is that this P is exactly the set of functions in A such that the order along E of F is greater than 0. So that's the same thing as saying that you look at the maximum ideal of YE intersect A. Because the maximum ideal evaluation ring is exactly those rational functions on the variety, which has order greater than 1, greater than 1. Yeah, so that's what the center is. Okay, so going back to this, now we are done, because what this means is that, in particular, and this is part of the statement, is that when I look at the rational map, is a birational map from there to X. All these maps are birational. So this is an isomorphism at the generic point of EI. So there is an EI here, and this EI will map down to D also birationally. Okay. So now we can put these things together. So what do we have? We have a divisor D. We have a birational map to some EI. And now EI has a fibration of a WI minus 1. And if I take EI to be the first integer for which I have this property, this birational map with D, then what I see here is that this map is generically a PR bundle with R greater than 1, because it's a fibration. And what about this WI? WI minus 1, the dimension is going to be at most 2, because the dimension of EI is, let's say, is a family of threefolds. The dimension of EI of D is 3, so the dimension of EI is 3. But now this map is a fibration, because I'm assuming if this is, if we take, let me write it here. I'm going to take this EI also such that WI minus 1 is a proper close subset on the next one, on the previous one. So the dimension has to be smaller. Okay, so now what do we know? By assumption, this is rationally connected. So this implies that this guy is rationally connected, is birational, but now I have a dominant map. So this implies that this guy is rationally connected. And now here's where we use a dimension. Rationally connected in dimension almost 2 is equivalent to rational. So now this WI minus 1 is rational. But this, because I have a projective bundle over it generically. So EI is rational. And therefore, we see that D is rational. So it's a pretty simple thing. Okay.
So may I ask a question?
Yes.
I don't understand. What about, so you said that you have to make this resolution, sort of resolution to go from D to EI, right?
Yes.
But what about if you don't have to do it, right?
Okay. So I forgot to discuss the simple case. So I forgot about it. So let me go back to that. Yeah, good point. So let me erase this part. Let me add a line. So if W is equal to the fiber, which is the fiber, let me write it T equals P1, Pn, then we're done. Because that means that D is actually birational to this fiber. So assume the W is strictly contained inside the fiber. And then I need to do the blobs. Yeah, that's a good point. I forgot that. Does it answer the question, right?
Yes, still I am a bit confused. So why if W, so if W is strictly contained in the fiber, so it could be a component, right, of the fiber?
Well, but then this is a fiber of this projective space T over T, so it's irreducible. So the point is that, let me draw a picture. Maybe let me draw a picture again. So on one hand, on the one side, I have this family of varieties, which degenerate to something which has many components. And D is one of those components. This is X. 20. On the other case, I have a product. And over the point T, on this case, this is my PNT. And this is just a projective space. Now the question is, one way of thinking about this is I start blowing up and then I blow down, and I want to see where D maps to. If D maps to this to the whole fiber, then under this process, this map is birational. So I give a birational map from D to Pn, and this shows rationality immediately. What is complicated is that the image of D, drawn in yellow again, vision D inside Pn might be some smaller set. So D might be contracted under this process of blow up and blow downs.
Okay, now I see.
Yeah, and then this is what the proof actually argue that you're still okay, because at some point when you contract it, there is a point when you contract D where it has to contract onto a smaller dimensional variety, and then I use a rational connectedness to conclude that this variety has to be rational because now it's small, it's almost a surface. And this map is a projective bundle, and therefore.
Yes, okay, now I see.
Rational. In fact, I want to make a remark here, is that, so if we could use resolution for singularities plus the weak factorization theorem, to write this proof. And probably that would have been more transparent what's going on here. Because that is really a sequence of blow-ups or smooth blow-ups and blow-downs. And I see what happened to D. Every time I blow up, the proper transform of D is still there. But when I blow down, there may be a point in this process when I blow down D contracting it. And then it is where I apply this observation about rational connectedness implying rationality. So it would make the proof more clear. So the advantage of the above proof is that it only uses this observation, this lemma of Zariski, which is very general, so it also works. In positive characteristics. So in fact, this theorem holds in all characteristics. I just wanted to mention this. By replacing the letter RC with the letter SRC, where S stands for separably. So what we do is that when we look at a map from P1 to a variety joining two given points, we ask this map to be separable. So if instead of looking at a rationally connected locus, you've got a separably rationally connected locus, then you can actually you get the same conclusion. Okay, any questions on this? So let me finish now. At the end, actually, I fill up the whole hour and a half. But let me finish with an example. So this example is to show that the last theorem is optimal, in fact. So it fails for n greater than 4. So the example here is a simple example. It's not very different from the degeneration to a conic over elliptic curve. So this example actually was constructed with David and Fusi. Our construction was conditional. And in fact, it was conditional to a theorem that actually was proved later by Totaro. And so the example then was eventually included in Totaro's paper. So the example is very simple. So I'm gonna start backwards now. I'm gonna start with the projective space and I try to construct X. So you start with P1 cos P1, so P1 cos Pn. Let me actually give a little bit more space here. And which is a map down to P1, so T1 is P1 in this case. And I want to construct a new fibration, which I'm going to call X. I do as follows. What I want to do an elementary transformation. Where I blow up something in a fiber. And then I blow down the fiber, the proper transform of the fiber. So this elementary transformation, of course, we're very used to compute them on when n is equal to 1. So you start from P1 cos P1, and then you blow up a point in the fiber, you blow down the proper transform, and you end up on a F1, and you do the same thing. You might go back, or maybe you go to an F2, and so on. So you can move from one irreducible surface to another. So by now, what we're going to do here is that now we allow a bigger dimensional fiber. So this map here is going to be the blow up a smooth hypersurface V inside a fiber. Sorry. of degree. I'm going to take the same degree n. It's not necessary, but that's in a fiber Pn. And now we do another n. On the other side, and we contract the proper transform of the fiber to a point. Okay, so let's see what happens here. So I'm going to draw now the same diagram drawing the pictures of what we have. Okay, so on this side, I have a fibration in projective spaces. So all the fibers are projective spaces. And I look at the central fiber here. And what I do is that I'm going to pick up some hypersurface, which I'm going to call V. Okay, and this, of course, I have a P1 here, and I have some point here, maybe a point 0. Now what we're going to do is we blow up V. So when we blow up V, now the new family is going to have two fibers over 0. One is going to be the proper transform of the previous fiber. And the other thing is going to be the section divisor. Okay. So let me maybe call the fiber F. So this will be some F tilde. And maybe this is the section divisor. Okay. And now we're going to contract F tilde to a point. So what happened now? So outside, I still have this nice family of projective spaces. But when I go to the central fiber, I end up with a cone. So this X0 is going to be a cone over V inside. So the cone over V will live inside a bigger projective space. Let me maybe remove that since it's confusing. There's going to be some cone over that. Okay, so the key theorem here that was not available at the time is the theorem of Totaro, which is if n is greater than 4, then V is not stably rational. But X0 is birational to V cross P1. So X0 is not rational. On the other hand, however, V is rationally connected. And this implies that X0 is rationally connected. So this shows that maybe just two remarks, and then I finish. Maybe Totaro and then Perry work out more examples. Where X0 has milder singularities. I mean, our interest in this question was just an example where the central fiber is rationally connected, but then the focus actually shifted from the understanding rational connectedness problem to actually quantifying how singular the singularities in the fibers are. If you take a hypersurface degree n, you get something which is not a log, which is scale t. But if you take a lower degree, for instance, you pick up examples which are only terminal singularities. And in fact, Terry was able to find an example. And what's remarkable, maybe also, that Terry uses a theorem of Wazan that was indeed available at the time, which is the first, I think it was the first theorem of this sort on failure of stable rationality. So the topic of stable rationality is very interesting. Maybe just to close with where we started from, I talked to you about these three theorems at the beginning of the class. This Skorsky-Manning, Clemens and Griffiths, and Artin-Mumford. And they use different approaches to disprove rationality. And each method has its own advantages and disadvantages. The advantage of the approach of Artin and Mumford is that they don't only disprove rationality, they disprove stable rationality, because they look at the Brouwer group, and the Brouwer group is a stable birational invariant. So if it's non-trivial, then it remains non-trivial. So the problem of that approach is that it's very hard to compute in general. And what was very clever in the Wazan approach is that she wants to use some degeneration, which fits very well with this part of the talk of the lectures, and to some singular, maybe let's just say, maybe you start with an hypersurface, you would look at a double cover. So you start with a double cover and you degenerate until the double cover acquires some ordinary double point. Then you resolve the ordinary double point. Because the ordinary double point is not very singular, like these birational singularities, if you like, it doesn't affect the computation very much. The problem is that you don't know how to control the Brouwer group under this process. So the idea, and I go back to Wazan and before, actually, Colliot-Hélène, maybe other people as well, is that you should not just look at one single group, the Brouwer group. You should look at something bigger, which is this ramified cohomology, and of which the Brouwer group is just one piece. And then what you can prove is that under these degeneration methods, this ramified cohomology is trivial if and only if it's trivial after degeneration. You don't know exactly where the triviality is going to jump from one piece to another piece. And but this one allows to apply these degeneration methods to disprove rationality. And with that, I think I said all I wanted to say. So I'm open to questions.
So one thing about that rationally connected thing.
Yes.
So if it's rationally connected, because if you have 2 points, then you can identify they're an open set with an open set of Pn, and then you can just connect them, right?
That's right.
And that's the reason why they need to be chosen to be very general, because they need to be like in the same open set that we identify with the Pn.
So there is a distinction between general and very general. So general just means is away from finitely many closed conditions. Very general, you need to allow count to be many. It's just natural to look at very general as a condition, because when you look at a space of rational curves, you have rational curves of various degrees. So don't think about the rational case. The rational case, as soon as you have a rational map, that's you just look at things coming from lines, that's a bounded degree. But you want to look at all families of rational curves. So this again is a Hilbert scheme. So you need to have, you have countably many families of rational curves. And when you degenerate, you need to worry about this degeneration. In principle, countably. I mean, I'm not 100%. I would have to look again. Just come up naturally in the construction of this equivalence relation. I mean, on the top of my head, I don't have an example of a variety where I can connect two very general points, but I don't know how to connect two general points.
Okay, no, but it may be okay. I understand. Okay, right. Thanks.
Yeah.
Tommaso?
Sì.
Can I ask a quick question?
Yeah.
These techniques that you mentioned have been probably attempted for the cubic fourfold, I guess, because it is the natural. So can you say a few words about why they failed for the cubic fourfold, or if there is hope in that direction?
Maybe I can stop sharing. Yeah. So cubics hypersurfaces. The problem of rationality for cubic hypersurface is very hard because there's just not enough room to do much. As soon as you degenerate to something with a singular point, that's rational. So that's rational. Let me just think for a second. Yeah, it's rational, right? Because if I have a cubic hypersurface with one singular point, there's a double point, the projection from that point will be generically a rational degree one map to a projective space. So, all these techniques again use degeneration methods. The idea is you degenerate to something singular, and then from there you compute whatever you need to compute. At least everything coming out from this approach started by Uzan. But because of the singular point on a cubic hypersurface just give you something rational, if you want to disprove rationality, it means you already lost your at that point. From there, even you don't get anything. Actually, it's not true, because in fact, one can say, okay, what if the total space is rational, and maybe their singularity is not be rational, but and then maybe you can try to get a contradiction that way. But again, a singularity starting from a cubic equation, it cannot be too bad. So it's just not enough room to do to apply any of these methods there. Totaro's theorem is quite strong, and then in fact it was actually later improved by Schreider. So you get a lot of degrees as a dimension grows. The number of degrees in which you disprove this stable rationality get larger and larger. Maybe I should actually mention, to be precise, you don't prove that are all stably not stably rational. You prove only that the very general one is not stably rational. Because when you get a conclusion about after degeneration, you want to go back. You don't get a conclusion for every fiber. You just get a conclusion for the very general fiber. So maybe that's something I should have mentioned. But yeah, it doesn't work for degree three. Degree three remains one of the big, understanding rationality for cubic hypersurfaces is one of the big challenges, I think. Of course, in dimension 4, that's a famous setting of study. But in higher dimension, I think very little is known, right? I mean, there's some obvious construction in I don't know if it's even or odd degree, even or odd dimensions. Maybe some of you remember. that you can do easily using linear subspaces. But beyond that, I don't think much is known.
But is the cubic threefold stably rational?
Yeah, I don't think it's known. I don't think I might be wrong. You know, I'm not really a super expert on the stable rationality that I know every result in the literature, but I don't remember seeing anything about that.
Because if you take a cubic fourfold with the triple point, that's birational to a cubic threefold times P1. And if the cubic threefold is not stably rational, then the cubic fourfold with the triple point would not be rational. This would give some.
Yeah. But
So
yeah, at some point, I actually play with these kind of constructions. You know, after the Kontsevich and Schinkel paper on with this B rationality points idea, I played a little bit around this. Then I discovered that in fact, whatever I was thinking about was already been done by Schreider better. I mean, the point is that one can ask whether one can actually get away without computing any ramified cohomology or this kind of invariance, just using this Schinkel, this Kontsevich-Schinkel approach to get some interesting examples. So that's what I was thinking about. But so you go a lot from, for instance, again, for this kind of construction, you have something in certain dimension, certain degree, you want to bump up dimension, bump up degree, try to get some sort of inductive approach. I couldn't get much out of it though.
Okay, Thomas,
I mean,
thank you very much for all.
A pleasure, and
Pleasure for us.
very good.
Thank you,
So,
Tommaso. You have opened parallel worlds to us. So thank you so much for your kindness, your how to say, precisione, non mi viene adesso in inglese. Thank
Ma
you
siamo
very
tutti
much
italiani, mi
siamo
sa
tutti
adesso.
italiani, parliamo un po' italiano.
No,
Senti,
no, c'è qualcuno.
magari chiudo la registrazione. Where is it?
Ok, ragazzi, io vi devo lasciare però.
Sì.
Un saluto.